All right, welcome. Today, we're going to tackle a topic that, let's be honest, trips a lot of people up in algorithm analysis, solving decreasing recurrence relations. But don't worry, we are going to learn an amazing shortcut that's going to save you a ton of time and, frankly, a lot of headaches. Have you ever found yourself just staring at a recurrence relation, like one of these, trying to substitute and expand it over and over again, just hoping a pattern will magically appear? It feels like you're stuck in the weeds, right? Well, what if I told you there's an elegant, almost instant way to get the answer? Because there is, and that's exactly what we're going to cover. So here's our game plan. First, we'll talk about the recurrence puzzle, why these can be so tricky. Then I'll introduce the master shortcut. We'll break it down into 3 simple rules, see those rules in action, and finally, we'll do an exam-ready recap to make sure it all sticks. Sound good? Let's jump in. All right, first up, the recurrence puzzle itself. Now, these things are absolutely fundamental when we analyze recursive algorithms, but let's be real, solving them by hand can be a total pain. Look, the old school way, using substitution or recursion trees, it definitely gets the job done, but it involves a lot of tedious algebra and you have to be really careful to spot the pattern. That's not ideal when you're short on time, like in an exam or a technical interview. And I'm sure you've seen some of these common patterns before. You might even have a few of them memorized. But who wants to have to derive these from scratch every single time? There's got to be a more systematic way than just hoping you remember the answer. And that's what we're here for. Okay, enough complaining about the problem. Let's talk about the solution. It's time to introduce you to the master shortcut, a special version of the Master Theorem that's built specifically for these decreasing functions. So this right here, this is our blueprint. Anytime you see a recurrence relation that fits this general form, you're in business. We call it a decreasing function because the problem size n shrinks by subtracting a constant b, not by dividing. If your problem looks like this, our shortcut will work. So let's just quickly break down what these letters mean. A is just the number of recursive calls you make at each step, b is how much you're shrinking n by each time, and f of n is just all the extra work you're doing in that step, besides making the recursive calls. Simple? So how does this whole thing work? Well, this is the really cool part. The entire solution, the entire time complexity, it all comes down to one single variable, the value of a. There are only 3 possibilities. That's it. Case 1. If a is less than 1, think about it. The recursive work is actually shrinking. It's becoming less important. So all that really matters is that extra work, f of n. Case 2. If a is exactly 1, we make one recursive call each time. That means we're doing that f of n work about n times. So the complexity is just O of n times f of n. And finally, case 3, if a is bigger than 1, we're creating more subproblems than we started with. This leads to exponential growth, and the complexity is dominated by that branching factor. It becomes O of f of n times a to the power of n over b. 3 rules. That's all you need. Okay, theory's great and all, but let's see this thing in action, right? Let's go back to those problems we started with and see if we can solve them in like seconds. First up, t of n equals t of n minus 1 plus n. Let's run it through our system. Okay, step 1. What are our parameters? Looking at the formula, a, the number in front of t, is 1. B, what we're subtracting from n, is also 1. And our f of n is just n. Since a is exactly 1, we are squarely in case 2. The rule for case 2? O of n times f of n. We just plug in our f of n, which gives us O of n times n, and that, of course, simplifies to O of n squared. Done. No messy substitution, no guesswork. All right, next up, t of n equals 2 times t of n minus 1 plus 1. I bet you can already spot which case this is going to fall into. Same process. A is 2, b is 1, and f of n, well, it's just a constant, so it's 1. Since a is 2, that's bigger than 1, so boom, we're in case 3. The rule is O of f of n times a to the n over b. We just plug in our numbers, O of 1 times 2 to the power of n over 1. And just like that, we get our answer, O of 2 to the n. See how fast that was? And that is the real magic here. You see what we just did? Instead of going through all that tedious manual work, the theorem lets us turn a complex analysis into a simple pattern-matching exercise. Find your A, find your case, and you've got your answer. All right, let's wrap this up and lock it all in. This is your exam-ready recap, the stuff you absolutely need to remember. Think of this as your cheat sheet. It's super simple. Is a less than 1? The answer is just the work function O of f of n. Is a exactly 1? Just multiply that work function by n.
And if a is greater than 1, that's when you bring in the exponential term. That's all there is to it.
So if you remember only one thing from this, remember this. When you see one of these decreasing recurrence relations, the very first thing you do is look for a. That one little number tells you everything you need to know and which of the 3 paths to take.
And there you have it, a really powerful, really fast tool to add to your algorithm analysis toolkit. It just goes to show that even the most complicated-looking problems can sometimes be solved with a simple pattern. So my question for you is, now that you have this shortcut, where else can you apply this kind of thinking to save yourself some time? Thanks for tuning in.